Before starting the academic discussion and particular portion of your syllabus, I just want to show you something that have you ever confronted this kind of image? Okay, when you look at this plot, or you can say this image, so initially we don't observe a lot of things. If you ask anybody who is a layman and he don't know the ABC of spectroscopy and ask him what is this, then most probably he will answer that a young kid has started writing, learning writing of, and his age is her age is 5 or 6 years. So maybe that is a haphazard manner he had drawn a line, but that's not the answer. Okay, basically there are a lot of hidden information in this image, in this plot. And what's this? You people have studied for a long time. That is cyclohexane. That you have studied what is cyclohexane. So spectroscopy can tell us about a specific compound that, okay, this is your specific compound. So if there is any impurity in the compound, there must be the peak shape must be not the same as it is now. But if you got a spectra like that, only a single spectra like this, then it means your compound is pure. So the first point you should keep in mind that this kind of information that you are obtaining from a spectra, we call them interpretation of spectra. We look at the spectra and we understand and recognize the peak. Okay, this peak which is lying at here, you can see here. Okay, okay. Now here you see here this peak. So this peak is you see for sp3ch stretch, and here is also a peak sharp peak over here. Here you don't need to memorize, you don't need to remember these values at the moment, okay? But here I just want to show you that how it look like. So one is this interpretation of spectra. Okay, let's move forward and another one. When you look at this one, okay, this is much more complicated as the previous one, because in the previous one there was certain peaks, but here the number is increased, and that is the spectrum of 3-methyl 2-butanone. And here again you see there are a lot of CH stretch and carbon double bond stretch, a lot of other peaks. But if you just thoroughly check one by one, so there is a regular procedure for understanding of interpretation of the spectra. Okay, that's the second one. Now when you look at this one, so at initial stage, I'm sure that you will face a lot of problem in looking to this picture. But when you just focus on the images and you compare both of them, you see that there is some difference. And that difference, you can easily understand that here, there is a sharp peak at almost 1700, below than 1700. Okay, but in this, there is no sharp peak over here in this image. Okay, again here, you can see here a peak and it have a shoulder as well. But in contrast here, we don't see. So it means these are two different things. We can easily understand. Okay, but when I interpret the spectra, both of them are pentene. Is it not very amazing that we can easily understand? Most of my young students that ask the question, sir, you people are using this cis trans. How one can understand and recognize that this is cis and that is trans? If I just rotate this like that, it is a 3D image in the air, and anyone can name that. So how you can see that? And then they crack a lot of jokes that chemistry is not real. Basically, we don't have understanding and we don't reach to that limit, that level that we can easily interpret the spectra. Now you have that level and you can easily understand that and you can easily interpret the spectra. But again, I'm repeating the point that today, and particularly in this class, we are not here to interpret the spectra. Okay, that is just for the sake of information and just to make a base for spectroscopy. I'm telling you that just you can look at both the images. They are not similar, but both of them are the same compound. The only difference is the above one is cis one, below one is a trans compound. Okay, let's move forward and look at this spectra. This is a different kind of spectra, and you can see here there are some sharp peaks, but that is totally different from the previous three slides. Here you can see it's written 111, here is 200, and here is 220. You will again confuse that what is this? Okay, I'm not going to explain it what is 111, what is 200, what's this written here 2D degree. I'm not going to explain that the terms. I'm just telling you, you can look at the spectra. So can you see that there are sharp peaks? Sharp peaks is, you see here, that is a sharp peak. Here, this is also sharp peak. This is also sharp peak, and this is also sharp peak. If here it's like a broader peak, okay, let me just draw by pen, then you can understand. If it was like this, then we cannot say it's a sharp peak, but it have a single tip like this, then we say it's a sharp peak. Here at 220, again it's a sharp peak. If it was like that, we cannot say it's a sharp peak. So now it's very easy for us. When I look to this kind of spectra and there are sharp defined peaks, then basically this is XRD spectra. So then we understand that our compound is crystalline in nature. Material that we had recorded the spectra for our material is crystalline. But if it is like this, the spectra is this one is, and the other one is also like this. So then we can say, okay, material is amorphous in nature. There is no crystallinity. So from XRD, we can easily understand that either we prepared the material, is it crystalline or is it not crystalline? So again, it's good information, and there is a lot of information in just only looking to the spectra. For example, you are in the lab and you are preparing some nanoparticles. Nanoparticle are those kind of material whose size is in the range of nano range. And you know nano range is 10 raised to the power minus 9 meter. Okay, this is called nano range. So if any material is ranging from 5 nanometer to 100 nanometer, we call them a nanomaterial. And originally this is the spectra of palladium nanoparticles. So it means the particle size is in the range that I have written here, 10 raised to power minus 9 meter or nanometer. So this range, the particle lies in this range. So is it not very interesting that we just recorded the spectra and we understand the particle is crystalline in nature? And you know, you have studied in your previous classes what is crystallinity and what is amorphous. So there is a lot of interesting information. And you know about that we cannot see a particle of 10 raised to power minus 9 meter. In the nano range, we cannot see the particles. If we had already studied in the quantum mechanics, the nano range and angstrom. So in the nano range, we cannot see, but still we can 100% confirm that either it is crystalline or it is amorphous in nature. So just looking to the spectra, you can understand. So till now, we understand two different type of things. The first one, when I look to a certain kind of spectra, then I can understand which type of compound this is. The second one, I can easily differentiate between two isomers just by looking to the spectra. And the third one, we can easily take the information of crystallinity and amorphous nature just from the spectra. The fourth one, we can take also the information of purity, that either our compound is pure or not. We can understand from here these different kinds of spectra. Now look at here. This is a very interesting information that I have done during my research work. That I prepared a compound that is nickel OOH. Then I added iron in this compound. Okay. Basically, these are sheets. These are nano sheets of nickel OOH. And when I incorporated iron in that nickel sheets, then of course I cannot see iron with my naked eyes. And you know about that, I cannot see. How I can see that iron is inside that sheet or not? When the sheet is in the nano range, that I cannot even see with my naked eyes, that is the limits of the sheet. For example, if you have a sheet that is your carpet, that is also a sheet, yeah, maybe by 12 by 12 square foot, then you can easily observe it with your naked eyes. But if I have a nano sheet and the range of that nano sheet is 100 nanometer, then I cannot see with my naked eyes. But I can understand and I can measure the length of that sheet by using different techniques, analytical techniques. For example, the first one, I can easily understand that what's the shape of that sheet from SEM, scanning electron microscopy. The second one, I can easily understand that how much is the length of that and what is the width of that and how much is the height. Then I can easily use the atomic force microscopy for that. Okay, I'm not going to go to the detail, then you will get a little bit confused. But here, that I'm just telling you that just by looking to the spectra, I can easily understand that, okay, iron is incorporated. You see here, the iron is, I have added 0.1, that's molar ratio. 10%, you just consider it's 10%, that is 20, 30, and 40. Just for the sake of simplicity, I'm just telling you. Now, this pentagon, when you look here, this basically representing the iron in the spectra, because I cannot write Fe everywhere. This will be seems a messy and not attractive image. So that is why I have just put a pentagon here. Here you see that it's a flat line. That is a flat over here, almost flat. But here we see here is a peak like this. And here again there is a peak like here. And there is another peak over here like here. So you can just easily understand that there are different peaks. Rest of the peak are the same. Everywhere you see that what the peak that I have just by this triangle and this star, you can easily understand that. And this star, okay. And now this is a different star which have I expect that it have how many arms it's have, almost 12. Okay, so this these are the same, common in all spectra, but the one which is a new that is the new one come from here. Okay, if I just want to zoom it a little bit, okay, then how it will look like, you can just look here, that basically this red color, that is blue, the pink one and the green one is the iron added spectra. I have just zoomed because I'm just giving you the look. It started from a range from 0 to 1000. Okay. Now the next one that I'm going to show you, I have just want to zoom this portion, this one. This portion I want to zoom. And the reason for zooming of this portion, because I want to confirm that either is there any changes over here. So when I zoom this portion, you see from 700 to 740, okay? And once again, just coming here, is it from, yes, it is from, this is 700 and that is 800. Okay, so that is, it lies in this range. you can see here just in 700 to 750, almost in this range. So I'm just going to zoom this, and when I zoom from 700 to 740, I observe a very fine peaks who are here. You see, it's not flat. All the peaks, there are peaks over there. It means iron is incorporated over there. Okay. So just by zooming, I can easily understand that there is a peak or some changes after adding that, and that is iron. Okay. Maybe you can ask the question that, sir, how I can confirm the presence of that iron, that it is iron from the peaks. It's a characterization. So XPS, that the peak over here, that is 712, are almost, because that is 710, that is 715. So 712 to 713, this peak is for iron. So we can easily understand. And that data is well established data, already developed by a lot of scientists. They have worked hard and can easily, now we can easily measure, because we know the baseline. We just take our sample, go to the lab, characterize it, recorded the spectra, and then came to our office or to our room, and then just zoom it and check it one by one, compare it, and we can understand. Now here, you can also see here there is another peak that after zooming, I can see it very clearly. And the second one, I can see here another peak. Now this is at 850 and 860. So it's in between 850 and 860. It means 855, 856. Okay, now coming back to this original, 856. Now 856 is almost over here. But here, this is not very prominent over there. When it is not very prominent, that is the nickel peaks. Now then when I zoom it, then I can easily understand, okay, that's a very sharp peak. Not sharp peak, but it's a very clear distant peak I can observe over here. That is also a kind of spectroscopy. Till now, I have not told you that what I have used, which kind of analytical technique I have used in differentiating the isomers. That is another kind of spectroscopy. The second one that I told you, we can find out the crystallinity, or we can find out the purity. That was another kind of spectroscopy. And now this one that I'm telling you, that either this iron is present or not, that is another kind of spectroscopy. So these are totally different from one another. Okay. And that is also the same that we have just studied now. It's another big, during my work, I have done some research work on that. And these are also, you can see here that there is no peak in this range, okay, from 40, before, after 40. But here you can see after 40, you observe a peak over there, okay. And here, you can also observe a peak over here. Also, the position, and here there is a peak, you can see a green is common here. It's also common here, and it's also common here, okay. You can easily understand that is from 40 to 30, that's a similar thing. 40 to 30, that's a similar, this one, okay. But still there are some changes. So whenever there is a change in my compound, how I can understand that where the compound is going to change? So basically, when I add a material, new material, a foreign material, so the existence of that material I can easily detect by some kind of spectroscopic techniques. Okay, this is some very interesting results. When you look at here, just now I have told you that there was nickel OOH, and then I incorporated iron 0.1, 0.23. So then I see here, when you look at this spectra, it seems now, if you remember my previous discussion, so these are all sharp peaks. This is a sharp peak. This is a second sharp peak. I can easily understand. Okay. The two are very sharp peaks and common everywhere. But the second point that I can observe, if you just look at the line, okay, let me remove the circles. If you look at this line that I have drawn upon there, you see that this black is just on the peak over here. And it's shifting, the peaks are shifting in this direction. You see the peaks is like this. So there is some changes, almost 1 degree changes. So when this kind of changes happen, and that is XRD pattern, XRD spectra, then I understand, okay, there is a foreign material, iron incorporated in my compound. So these are the information we get. Okay, now I think till now you have a little bit baseline which is developed about spectroscopy. So what is spectroscopy? Keep in mind, what we have studied till now was just a background. That's not a part of your course. That's just, I want to tell you that you realize the importance of spectroscopy. That spectroscopy is one of the most powerful tool for analysis, and that analysis may be qualitative, may be quantitative. Okay, I'm not going to discuss it now, but you should keep in mind. And keep in mind the different examples that, okay, if I have cis compound, if I have trans compound, the spectra will be different. If I have pair compound, if I have mixture, spectra will be different. If I have crystalline material and if I have amorphous material, spectra will be different. If I added any oxygen, any oxide, and if I don't add any oxygen, spectra will be different. So it means I can easily qualitatively analyze the compound by spectroscopy. Now, what is spectroscopy? That's coming to this topic now. So spectroscopy is the study of interaction between electromagnetic radiation and matter. Okay, we know that in chemistry we are studying matter because chemistry is the study of all the materials, and sometimes you are studying organic compounds, inorganic compounds, uh, and sometimes you are synthesizing some compound in the laboratory. Sometimes you are taking compounds from the environment and from already plants and animals and studying in the lab. There are different studies. So the most easy definition that we are studying materials. Okay, so whenever there is interaction of material and electromagnetic radiation, and we studied it, this is called spectroscopy. Okay, because electromagnetic radiation in our environment, there are electromagnetic radiation. So you can ask this question, it's sir, every time there is interaction between electromagnetic radiation and material. So every time, everywhere is spectroscopy? No. When we are going to study that, in a particular proper arranged manner, we call them spectroscopy. So spectroscopy is the study of interaction between electromagnetic radiation and matter. Now this matter can be atoms, this can be a molecule, or this can be an ion. Okay, so there is no restriction that in spectroscopy you can only study atoms, because I told you just now that I used to add more iron, and when I added the iron, I find out and I observed that there is a observable change in the spectra, peaks that is shifting from one side to another side. So we can study atoms, we can study molecules. Just now I told you that if we have a cis compound, if we have a trans compound, we can easily differentiate by using spectroscopy. And we can also study ions. Like in one of the slides I showed you, that if there is any tungsten W ions that is coming are producing inside the compound, I can easily find out. Okay, just keep in mind that every material, that is atom, molecule, or ion, is associated with a signal. Now it depends upon on my analytical technique that which one I'm going to use. The signal will be created as it is. Okay, so it's very easy. Don't afraid of the subject. It's very interesting that it's just the study of interaction between electromagnetic radiation and matter. And the matter can be atom, molecule, or ion. Okay, now spectrum. What we have just seen now, the first slide, second, third, fourth, all of them were spectrum. Okay, now spectrum is a plot, and you see that of course it was a plot. On one side you see here, on one side you see that there was different numbers. On other side, there are also different numbers. So basically, just now we have studied that it is the interaction of light. So on your y-axis, you see that the light absorbed by the sample. And on your x-axis, it was wavelength of the light. So spectrum is like that. Okay, I'm just repeating again, it's not important that this case must be obeyed everywhere. That every time you will search for the wavelength, that where is the wavelength? It may be something else, some other things that may be interpreted in a term in the form of wavelength, but there's a very general definition that a spectrum is a plot of amount of light absorbed by a sample versus the wavelength of light. Now, the amount of light absorbed is called absorbance. And what will be the answer if the amount of light transmitted? So that will be transmittance. So it's very easy that we can understand the spectroscopy word by word, slowly and gradually. Okay, so we have studied two things. That it is the interaction of electromagnetic radiation with the material. And that material may be atom, ion, or molecule. And in chemistry, we studied their things a lot, that what is atom, what is ion, and what is molecule. We know about that. So the other thing is electromagnetic radiation. So electromagnetic radiation, the most, if anybody asks you what is electromagnetic radiation, so the most easiest and simplest definition is it's a form of energy. Okay, the first point. Electromagnetic radiation, what is electromagnetic radiation? It is energy. So spectroscopy is the study of energy and material. Okay, very general. Which kind of energy? A kind of energy which contain both electrical and magnetical properties. They have a characteristic, magnetic characteristic and electric characteristic. Now, before James Clerk Maxwell work, different scientists believe that electricity and magnetism are separate forces. But then they unified and they named it the electromagnetism. Okay, so the study of electromagnetism deal that how electrically charged particle interact with other and with magnetic fields. So that is just the definition of electromagnetism. Basically, we are studying electromagnetic radiation, so we should know a little bit about the basis of electromagnetic radiation. Now, electromagnetic radiation, as I told you, that it's a form of energy. And that form of energy, they contain both the portion, both the characteristic, that is electrical characteristic, and they have magnetic characteristic as well. The electric and magnetic field in an electromagnetic wave oscillate along the direction perpendicular to the propagation of direction. Now, that you have studied in your physics in the foundation of science, I think first or second, that how electromagnetic radiation propagate and what's the angle between electric oscillation wave and magnetic oscillation wave. So they are 90 angle, okay, and that is the shape of that waves. Here you can see the magnetic field is represented by blue color lines. Okay, that's a straight line here you can see, and that is a magnetic field. So you see here that is a magnetic field. It's a complete wave, okay, and it's propagate in this direction. Just consider that it's coming in the direction like this one. Okay, what about the electric field? The electric field is represented by that red arrows. You see here the red arrows represented electric field, and that is a propagation direction. Both the waves, electric and magnetic, they are propagating in this direction. What about the direction, the angle between them? So it's very obvious, very clear that the angle between magnetic radiation and electric radiation is 90 degrees. So both of them are perpendicular. And this kind of wave, we call them electromagnetic wave. Okay. Now, electromagnetic spectrum. Keep in mind, electromagnetic spectrum, they have a shorter wavelength and they have a longer wavelength. So what is meant by shorter wavelength and what is meant by a longer wavelength? It's very easy. You know about the frequency and wavelength relation. That when the wavelength is increased, frequency, when the wavelength is increased, frequency will be lower. And when the wavelength is decreased, smaller, then the frequency will be higher. Or you see here, a shorter wavelength means frequency will be higher because the cycle can pass in a shorter amount of time. And that's, you know about this. So that is why I'm not going to take more time on that subject. Similarly, a longer wavelength has a lower frequency. So from this slide, if you remember 2 points, that shorter wavelength will have higher frequency and longer wavelength will have lower frequency. That's very easy, okay? Now, there are different terms that we are using while studying spectroscopy or electromagnetic radiation particularly. What's frequency? I'm sure that all of you know about the definitions, but just I want to remind you that what you people have studied in your previous classes. Because when we studied some things long ago and we don't go back and don't study it again, then sometimes that images that exist in our brain become blurred, and we cannot even sometimes differentiate between two similar definitions. If there is something common, then we got confused about that. So that's the reason that I'm just revising that thing, different terms. Like frequency, it's number of waves produced each seconds. So number of waves passing per second, we call them a frequency. And what is a wavelength? So the distance between two successive waves. And just now I have told you, if we just draw a wave, like let's suppose it is a wave like this. Okay. So if I just started from here, that is my start initial point. So when I reach it again to this point, so one wave is completed. Okay. If I reach here, it's one wave. Okay. If I started from here, then my wave is going to complete over here. Okay. This drawing is not very fine, but okay, I'm sure that you can understand that. Okay. Now, what is wavelength? So the distance between two successive waves. It's basically meter is a SI unit, so I used it here. For frequency, we will use hertz. What's amplitude? Is the maximum distance a wave extend beyond the middle point. And you know about that. If we just plotted a wave on the x-axis and the y-axis show its absorbance. So as the distance covered on the y-axis, we call them amplitude. It's very simple. Okay, now here, this figure you can easily understand because it's well drawn. Now here, if I just started a wave, it's coming along a direction like this. So here, it's the bottom and here is the peak, okay? So when I'm just starting from this point, from this bottom, and I go through like this, so I reach to the bottom here, okay? So now this wavelength, this is called the wavelength, the distance from one trough to another trough. It's called wavelength, and are the distance from one peak to another peak. So these are called the wavelength. Now, and you know that here the formula, it is the V, velocity, speed of the wave is frequency multiplied by wavelength. If I just represent frequency by F and wavelength by lambda, so F by lambda, we call them a frequency. Okay, so that's very easy and very interesting. Okay, what's electromagnetic spectrum? So electromagnetic spectrum, I told you it ranges from shorter wavelength to a longer wavelength. Shorter wavelength, just keep in mind, is gamma rays, and longer we call them radio waves. Okay. The second point, there is also a visible portion, because when something is started from a lower value to a higher, so of course there must be some range 400 to 700, and we call them a visible region. Okay. The shorter wavelength begins the blue end. They are going just to connect the shorter end, because beyond 400 we call them a shorter, and after 700 we call them a longer. So the shorter wavelength begins with the blue end of the spectrum and the longer with the red. So it means that this visible spectra, they are going to connect the shorter and longer one. Okay, the wavelength between 400 and 200 make up the near ultraviolet region. Near UV, we call them near UV region of the spectra. Okay, and the wavelength above 7 nanometer, approximately to 2000, is ultraviolet region. Okay, now here you can see different regions, that if I'm started from here, because that is a shorter wavelength, 10 raised to power minus 11, then longer 10 raised to power 9, then 10 raised to power minus 7, minus 5, minus 3, and all of them are in meter. Okay, so if I'm just coming along from left to right, so the wavelength increases and frequency will decreases. Okay, so when the wavelength increases, frequency will be decreases. What do you think? Which of the radiation? That is the gamma rays, and then X-rays, then UV, then visible, just in this range, and then IR, microwave, and radio. Which one will have high frequency? If I'm just coming from this left to the right, on the rightmost side, that is 10 raised to power 3, will have high frequency, or 10 raised to power minus 11. Just think for a while. Okay, it's very easy. And then you can understand that if I am going to select high energy radiation among all of them, which one I need to select? If I need a high energy radiation, and energy E is equal to h nu, so it means energy is proportional to frequency. If I am going to select a radiation which will have high energy, so it's very simple. I need to select a high frequency radiation. So which one of them have high frequency radiation? And frequency and wavelength have also relation. It's not a direct inverse relation. So higher frequency must have if we need a higher frequency, the wavelength must be very low. And if the wavelength is very high, the frequency must be very low. So they have inverse relation. Okay. And now the whole broader spectra is become clearer now, that gamma rays, X-rays, then ultraviolet. So if I'm just in between here, infrared and ultraviolet, there is a visible. And that visible, if we just zoom it, then we can see here. And the line that I have used, that here the infrared is connected on the red side, and here you can see on the pink or bluish side of that is ultraviolet radiation. Okay, that is just for the sake of information. There is no some technical reason for that that I can tell you why we call this ultraviolet and why we call IR. Basically, these are on the basis of ranges that we know. And shorter wavelength and higher frequency and higher energy will be on this side, and longer wavelength, lower frequency and lower energy on the our right side. So now I can easily understand that on our right side we have a longer wavelength, but we have a lower frequency and lower energy. And from this, this is a wavelength demonstration of all these. You can see here is a longer wavelength, because if I just count it from this point to this one, this is a long range. But if as I am moving on this side, wavelength decreases. And when the wavelength decreases, the frequency increases. And frequency increases, energy increases. It reaches to a maximum value when I reach at the left hand side. When I reach at the left side, that's the gamma rays. So this is just an introduction. Now here, the diagram below show 4 waves. You see here is a gamma rays, infrared rays, ultraviolet rays, and a microwaves. Now, these 4 radiation, all of them is a type of electromagnetic radiation: gamma, infrared, ultraviolet, micro, uh, but not to the scale. Which kind of have a greatest frequency? When you just look at here, and I'm sure that everyone can answer this because it's quite easy and quite interesting. Okay, now when I look at the broader spectra, the whole spectra of electromagnetic spectra, so you can see here that we have radio waves, microwaves, IR, visible, and gamma rays. That is the wavelength in meters. Okay, so 10 raised to power minus 3, then minus 2, then minus 5, minus 6. What does it mean? As I'm going in this direction, I have just reversed the direction, that you can just understand that, not to memorize that. Because in the previous slide, I have used the ranges on the left hand side, that is a longer wavelength. And then sorry, on the right hand side I have used the longer wavelength, and on the left hand side I use the shorter wavelength. But now I have reversed the image. The reason behind that, you should not keep in mind that on the left side it must have shorter wavelength, on the right side. That has nothing to do. You have to just keep in mind that the shorter wavelength will have higher frequency, lower wavelength. The longer wavelength have shorter frequency, will higher frequency and have higher energy. You should just keep this thing in mind, okay? And then that is the frequency wise. You see here, frequency 10 raised to power 4, then 10 raised to power 8. So it means if I have to compare radio waves and microwaves, which one will have higher frequency? Microwaves. And the gamma rays have the highest frequency. Okay, if I just zoom this portion, just the visible, then I see that violet, blue, indigo, there's green, yellow, and red, different colors. Okay, so these are the visible lights. I think that what we had studied is enough for today's discussion, because that was an introductory lecture. And don't be terrified of this subject. It's really very interesting, and you will get a lot of meaningful informations and knowledge from that spectroscopy. Uh, and I think it's enough for today. Assalamu alaikum wa rahmatullahi wa barakatuh.